In this video, we solve problem 15.R.081 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use the divergence theorem to evaluate the flux integral and find the outward flux of F through the surface of the solid bounded by the graphs of the equations. We're given this as our field, and we're told that Q is a solid region bounded by the coordinate planes, that's the xy plane, the yz plane, and the xz plane, and a fourth plane, given by 3x plus 4y plus 6z equals 24. Now here's a reminder of what the divergence theorem says. It says the flux through the surface, where that surface is a closed surface, turns out to be the triple integral over the volume inside of the divergence of the field. Now this doesn't always hold. This holds provided the following conditions are true. Now if Q is a solid region and it has a closed boundary surface S, and S is oriented by an outward unit normal, so all the normal vectors are pointing out of Q, not into Q, and the field has components Mn and P, and Mn and P have continuous first partial derivatives in an open region that contains Q, so that's that solid region that we're integrating over, as well as its surface, that boundary surface of Q that we're calling S. I believe all of these hold. We're told that this is a solid region. It has a closed boundary surface S. It actually consists of 4 pieces, 3 coordinate planes in that plane. We can orient those planes with outward unit normals so that all the normal vectors are pointing out of the surface. And then the field is this given field. These are our component functions M, N, and P. I actually prefer component form. So rather than writing it that way, I'll write it this way: x squared times I hat plus xy times j hat plus z times k hat. Those are obviously continuous. They're polynomials in x, y, and z. So they have continuous first partial derivatives with respect to x, y, and z throughout 3-dimensional space. So they certainly have continuous first partial derivatives inside Q and on the boundary of Q. So that being said, rather than evaluating this surface integral, we can evaluate this integral instead. All we need to do is find the divergence of the field and sketch Q so that we can use our sketch to come up with appropriate bounds describing Q, and then we'll evaluate the triple integral. So let's start by computing the divergence of F. And remember how that works. The divergence of F can be thought of as that del operator dotted with F. Now the del operator is an operator that acts like a vector. It has as its components those partial derivative operators with respect to x, y, and z. Our field is this. And then we think of this like a dot product. If I were to take a dot product of 2 vectors, I'd multiply component by component, and then I'd add. So I multiply these 2 and add, multiply these 2 and add, and multiply those 2 and add. Now, when you're working with the del operator, it's not multiplication. Everywhere you would typically multiply, you're going to operate instead. So instead of thinking of this as this times x squared, I want to think of this as the partial derivative with respect to x of x squared. And then we add the partial derivative with respect to y of xy. And then we add the partial derivative with respect to z of z. And this derivative is 2x. The derivative of this is the derivative of a constant times y with respect to y, because we're treating all the other variables as constants. The derivative of a constant times y is just the constant. And the derivative of z with respect to z is, of course, 1. So the divergence turns out to be 3x plus 1. The next thing I want to do in order to set up this integral is sketch Q so that I can use my sketch to come up with appropriate bounds describing Q. So Q is a solid region. It's bounded by the three coordinate planes, the XY plane, the XZ plane, and the YZ plane. Now, of course, I'm just sketching part of those planes. This is like a floor and a wall, and then the wall next to it. So those are three of our boundaries. And Q is also bounded by this fourth plane. Now, the easiest way to sketch this plane is to find out where this plane intersects the x-axis, the y-axis, and the z-axis. And that's easy to do. All you do is let two of the variables be 0 and then solve for the third. So if x and y are 0, and we're on this plane, we have 6z equals 24. So z must equal 4. And if x and z are 0, so those guys are gone, we end up with 4y equals 24. And then we solve for y by dividing by 4, and we get y equals 6. And now let's let y and z equal 0. Then we'll have 3x equals 24. So we get x equals 8. So this tells me that this plane intersects the z-axis at 4, it intersects the x-axis at 8, and the y-axis at 6. And that's the fourth side of our solid. So our solid has this little triangle in the back as one of its boundaries. That's one part of S, the boundary of our solid region. And then it also has this triangle as one of our boundaries. It has this little triangle in the XY plane as one boundary, and then it has this other plane on top as a fourth boundary surface. So Q is the volume inside. It's sort of in this back corner of that first octant. So Q is the interior of that. Now it's easy to see how we would orient normal vectors outward. When we have this little triangle in the XY plane, you can put a normal vector going straight down. We have this little triangle in the YZ plane. You can have a normal vector going straight back there. This triangle in the XZ plane, you can have a normal vector going off to the left. And then this plane, I'm just going to draw that as a dot with a circle around it. That is a normal vector sort of coming out of the page at us like this. It looks like a single dot, like you can see at the end of my marker. That's a normal vector coming out at us. So those are normal vectors oriented outward. And each of those planes comprises part of the surface. The entire surface S is the union of those four planes, or those four planar pieces. Okay, so that is our solid region Q. Now we need to come up with appropriate bounds for X, Y, and Z. Now there are lots of different ways to do that. I think the easiest way is to let Z go from a function to a function. So from a bottom function to a top function, and then look at the projection onto the XY plane. And then we'll use our projection to come up with appropriate bounds for Y and X. So our first bound for Z is actually the XY plane itself. And we know that the XY plane is just given by the equation Z equals 0. So that's our bottom function. And then we want Z to go to a top function. I think we can all see that if we're talking about this little solid region in here, the top function is this plane, this one that's closest to us with the normal vector pointing straight out at us. And that's given by this equation. In order to write this as a bound for Z though, I need to solve this equation for Z. So we will subtract b3x and the 4y from both sides, and we'll divide both sides by 6. So 24 divided by 6 is 4. We get 3 over 6 is 1/2. And then 4 divided by 6 is 2 over 3 times y. So that is z equals some function of x and y is that top surface. So that is our upper bound for z. Okay, now to find the bounds for x and y, we need to look at the projection of the surface onto the xy plane. So it's that little triangle. So that's what we've been calling R. And it intersects the x or the y-axis at 6 and the x-axis at 8. And it includes that back corner. So the region R looks like this. Now you have options. You can let x go from a left function to a right function and let y go from 0 to 6, or you can let y go from a bottom function to a top function and let x go from 0 to 8. I think I'll do that. So y is starting at the x-axis, which is y equals 0, and it's ending at that line. Meanwhile, x is going from 0 to 8, so we'll do that part first, the constant to constant bounds first. And then this line, we can come up with its equation pretty easily. Y is equal to mx plus b, right? The slope comes from using rise over run or fall over run, since it's falling as we go left to right. So we go down 6 and over 8. That's our slope. And the y-intercept, that's where the line crosses the y-axis, is 6. So we end up with 6 minus 6 over 8. That's 3 times 2 over 4 times 2. Of course, the 2's reduce, and we get y equals 3/4 of, or 6 minus 3/4 of x. Now we could have also let y go from 0 to 6 and let x go from this function to this line, and that would work out just fine. But I would have to solve this equation, y equals 6 minus 3/4 of x. I'd have to solve this equation for x and get x in terms of y, and let x go from this function of y on the left to this function of y on the right. I'm not going to do that. I'm just going to stick with the bounds where y goes from a function to a function and x goes from a constant to a constant. Okay, so we've got everything we need. We sketched the region Q. We stated the appropriate bounds for Q. By letting z go from a bottom function to a top function, and then looking at the projection onto the xy plane and coming up with bounds for that. And now we're just going to substitute those into the divergence theorem. I'm using THM as an abbreviation for theorem. So we're saying the flux through the surface is the same as the triple integral over Q of the divergence of F. And Q can be described this way. Constant bounds go on the outside. It's the integral from 0 to 8 of the integral from 0 to 6 minus 3/4 of x of the integral from 0 to 4 minus 1/2 x minus 2/3 of y. And the integrand is the divergence of f. We calculated that earlier. It was 3x plus 1. Now this variable goes with these bounds. So we're going to integrate with respect to z first. The next variable goes with the next set of bounds. So then we integrate with respect to y. And lastly, we integrate with respect to x. So now we're here. And remember how this works. You want to evaluate the innermost integral first. So this doesn't have any z's in it. The antiderivative of this with respect to z is like taking the antiderivative of a constant. The antiderivative of a constant with respect to z is that constant times z. And then you evaluate from z equals 0 to z equals the equation of that top plane. And then when we substitute, we're going to get 3x minus 1 times the equation of the plane minus 3x minus 1 times 0, which is just 0. So really, we just end up with 3x. I said minus, I meant plus. 3x plus 1 times that as our new integrand. And then we'll evaluate the double integral over that little triangle. So we have the integral from 0 to 8 of the integral from 0 to 6 minus 3/4 of x of 3x plus 1 times 4 minus 1/2 x minus, and I'm looking on the last page, 2/3 of y. We're integrating with respect to y next, and then x. At this point, you can distribute if you want to. I think I would like to eliminate all these fractions. So what I think I'll do is I'll get a common denominator here. So I'd really like all of these to be over 6. I'll multiply 4 over 1 by 6 over 6, multiply 1 over 2 by 3 over 3, and then multiply the 2 over 3 by 2 over 2. And so I'll have 24 over 6 minus 3 over 6 x minus 4 over 6 times y. And then I can factor out the 1/6. I think I'll do that. I'll take that 1/6, then I'll bring it outside of my integral. And so I have 3x plus 1 times 1/6 times all of that. So I pulled the 1/6 out, and I'm left with this. Okay, now at this point, I think I'll distribute. Three x times this trinomial is 3x times 24. So that's 72 times x. And then we have 3x times negative 3x is negative 9x squared. And then 3x times negative 4y is negative 12xy. So that was this first term times the entire trinomial. And then we want to do 1 times the entire trinomial. So we just end up with 24 minus 3x minus 4y. And we are integrating all of this with respect to y. Let me see if I have any like terms. Got a negative 9x squared. And then I have a 72x minus 3x. So that's 69x, or plus 69x. I have a plus 24. Then I have a minus 12xy and a minus 4y. And I'm just choosing to organize everything this way. because all of these are constant with respect to y. So I'll get each of these times y when we integrate. And then these two have y's in them, so I'll have to use the power rule for those two terms. Okay. So we end up with this. Oops, actually I don't want to do that anymore. Now let's integrate with respect to y. All of this is constant with respect to y, so I'll bring down my constant. The antiderivative of a constant with respect to y is that constant times y. And then these two pieces, I can use the power rule. So I bring the negative 12x down, then I add 1 to the exponent, and I divide by the new exponent. Then I bring the 4 down, the negative 4 down, then I add 1 to the exponent, and I divide by the new exponent, and substitute y equals 0 and y equals 6 minus 3/4 of x. And then we apply the fundamental theorem. So we'll plug that y value in and that y value in, and we'll subtract. Of course, these can be simplified. That's a 6, that's a 2. Now this 6 minus 3/4 of x, I think I want to factor out a constant with that as well. I'll write that 6 as 24 over 4. That way we have a common denominator here. And then we can factor out that 1/4. So we've got 1/4 times 24 minus 3x. So that's what I'm going to replace y with when I substitute. Rather than using this, I'm going to use this. So we'll have 1/6 of the integral from 0 to 8 of negative 9x squared plus 69x plus 24 times y, which is this. And then over here, we'll have negative 6x minus 2, or let's say negative 6x plus 2, times y squared. So that's 1/4 times 24 minus 3x, quantity squared. And then when we substitute y equals 0, we just get 0 minus 6x times 0 squared minus 2 times 0 squared. So all of this is 0. So we really don't have to do anything there. And so now we're here. What a mess, huh? Let's see, how can we simplify this as much as possible? I think I would like to let's factor out the 1/4 here and one of those 1/4. Since this is squared, we can square the 1/4 and we can square that binomial. And I'm going to factor out a 1/4 from here and one of those 1/4 from over there. So we'll have 1/4 times 1 over 6 is 1 over 24 times the integral from 0 to 8 of all of this. So it's just a lot of algebra. Then we'll have a 1/4 left over. We've got a 6x plus 2 there. And then we've got a 24 minus 3x quantity squared there. Now I could do the algebra in line so that it's all being evaluated inside this integral from 0 to 8 with respect to x, but I don't think I want to. I think I want to simplify this separately. So let's do this first. I've got this trinomial times 24 minus 3x. And remember how you do that. You just take the trinomial and multiply by 24 and take the trinomial and multiply by negative 3x and see what you get. So I'm going to simplify just this part first. I have 24 times negative 9x squared plus 69x plus 24. minus 3x times negative 9x squared plus 69x plus 24. And I'm going to use a calculator for the arithmetic just because I don't want to waste too much time. So I've got 24 times 9 is 216, and then that's negative. So I have negative 216 x squared, and 24 times 69 is 16,000, or not 16,000, 1,656 times x, and then 24 squared is 576. And then this negative 3x times that is going to give me a 27x cubed. 69 times 3 is 207. So we have negative 207. X times x is x squared. And then 24 times 3, that's going to be 72. And we have a single x there. Okay, let me make sure. It's an x squared term, an x term, and a constant term, an x cubed term, an x squared term, and an x term. Okay, so that looks good. Let's reorder those. Put my cubic function first. And then I've got my two squared terms. So I've got 216 and then a 207. So that's minus 423 x squared. And then we've got this 1656 minus 72 times x. So that's 1584 times x. And then we've got the 576. Okay, that's just this first part. Now we've got to do the second part. Call that double star. I have negative 1/4 times 6x plus 2 times 24 minus 3x quantity squared. Now you may remember from algebra class that a minus b quantity squared is a squared minus 2ab plus b squared. If you're not sure about that, write this twice in FOIL. Outer times outer plus inner times inner is where that negative 2ab comes from. I'm going to apply that formula right here. So we'll have a negative 1/4 times this, and I think I'll factor out a 2 from that as well. That's 2 times the quantity 3x plus 1. And then this 24 minus 3x squared is 24 squared, which is 576, minus 2 times 24 times negative 3, or 2 times 24 times 3. That's 144x. And then negative 3x squared is plus 9x squared. Okay, and that 2 goes into the 4 twice, so we have a 1/2 here. And now you can take this 3x plus 1 and distribute it through this trinomial. So we'll do 3x times all of this, and then 1 times all of that. I have 3 times 576, which is 1728 times x, and then 3 times the 144. That's negative 432. X times x is x squared. And then we have 3x times 9x squared. 3 times 9 is 27. X times x squared is x cubed. Okay, so that's right. And then we have 1 times all of that. So we just write that down again. And then let's collect like terms. Put the x cubed term first. Then the x squared terms, I've got negative 432, and then a 9x squared. I have negative 423x squared. And I've got that 1728x minus 144x. So that's 1584 times x. plus 576. And we can take each of these and divide by 2, or divide by -2. Let me make sure my signs are right. Negative times a positive should be a negative. Negative times a negative should be a positive. When I divide a positive by a -2, I should get a negative there. Whoops. And a positive divided by a negative is negative. Okay, so that's my double star term. My single star term was 27x cubed minus 423x squared plus 1584x plus 576. Okay, so I want to add this and this together. So I've got 27 minus half of 27. So the result should be half of 27 times x cubed. And then I've got half of 423 minus 423. So I should have minus 423 over 2 times x squared. And then I've got 1584 times x minus 792. And that's going to be 792 times x. And then I have 576 minus 288, which is 288. Ah, that's a lot. That's our integrand. Remember what this was about? We were trying to find flux, and the way we were finding flux is by evaluating this integral. That was the last thing we needed to do. So we just simplified this part, and now we're going to integrate it from 0 to 8. Don't forget that 1 over 24, otherwise you'll get the wrong answer. So going back to our original line of thought. Add 1 to the exponent, divide by the new exponent. Bring the constant down. Add 1 to the exponent, divide by the new exponent. Bring the constant down. Add 1 to the exponent, divide by the new exponent. The antiderivative of constant with respect to our variable is the constant times the variable. And then we evaluate from 0 to 8. So we will have 1 over 24 times 27 over 8 times 8 to the 4th minus 423 over 6 times 8 cubed plus 792 over 2, which we could simplify, times 8 squared plus 288 times 8. And then we evaluate all of this at x equals 0. So we're going to get 0 minus 0 plus 0 plus 0. So we're just going to get a bunch of zeros there. So that's our answer. It's just not simplified. Of course, we could simplify it, but let's just use the calculator for the arithmetic. So we'll do 27 divided by 8 times 8 to the 4th. Now I know we could have simplified those 8s, that's fine. Minus 423 divided by 6. Times 8 cubed. Plus 792 divided by 2 times 8 squared. Plus 288 times 8. Take that answer and divide by 24 because of that 24 out front. So we get 224. And if you're saying to yourself, what is that? Remember where we started. We've got this field. It's acting at every point x, y, z in three-dimensional space, including the points inside Q and on the surface S, those four surfaces that make up S. We want the flux of that field through that surface. According to the divergence theorem, rather than evaluating these four surface integrals, so I'd have to do this surface integral plus that surface integral plus the back surface integral plus that surface integral, the divergence theorem says, don't do that. Just compute the divergence first and evaluate the triple integral over Q. So we did all of that. We got 224 what? Well, it really depends on what F represents. If F is the velocity of some fluid, this is the volumetric flow rate. So this is the amount of fluid moving through the surface per unit time. And that's volume. So this would be units cubed per unit time. So if the units for volume were meters and time was measured in seconds, this would be 224 cubic meters per second.